Start, please, and take a look at the first question. On your warm-up, it says you're given that line M is tangent to the graph of F at that point, and line M passes through that point. Write the equation of a line tangent to F at 2, 3. Well, what do you need to know before you can answer out that question? Hands up, please, if you can tell me what you would need to know before you can answer out what that question is. Something we need. It's the slope of the line. How are you going to find it? Okay, so what did you get as your slope? There you go. So I went through and recognized that I need to go through. I used those 2 points, and I found that as my slope. All of us should have been able to get that piece. The next thing that you need to know is you need to give the line tangent to that. Now, if it's tangent to it, that means it touches it once at 2 negative 3. Sam, what did you get as an answer for this, or what would you get? There's multiple correct answers. Who can tell me what they would get? What's that? What slope? Let's say it this way then, Sam. You're going to use y minus y1, right? Which point do you want to go through and use? Okay? So what would that be when you made that plug-in with that slope? I don't need you to get it in y equals 4. What'd you have?
Y minus 2 equals negative 5/3 x plus 1.
There is another point that you could have gone through and used. You could have also gone through and expressed it out using the other point. Those two lines are those two equations are of the same line, just different forms. When we give out lines in here, just so you know, we're never really going to be asking for them in y equals mx plus b form. Next one up, you've got to give the equation of a line perpendicular to the tangent line at that point. So if it's perpendicular, what do we need to change about it? Evan? So what's the slope of our new line going to be? 3/5. And what's the equation of our perpendicular line going to be?
Y equals something like that. Y equals 3/5 x plus 21/5.
Just give it out in y minus y1 form.
Y minus, or y plus 3.
Equals?
3/5 times quantity x minus 2.
There you go. Questions on that? Now, at the end of the period, we'll have you handed limits worksheet C in your work. Understand this. You should have picked up 2 sheets, 2 single-sided sheets. Or sorry, 2 single sheets. There's diving in number 1 that you're going to be working on. Is this it? This is going to be due for all of you. What day does it say on there? Due at the beginning of day 4, so you might want to put that someplace on there. Your work for this can fit right on it. These are the questions that are going to help you determine whether or not you're going to be ready to take the AP exam. There are 30 of these sheets. They're indexed out by topic. For which of the following does a limit exist? You go through and answer. No work needs to be shown there. You do need to show work out in 3 and in 4, or at least show what you're evaluating out in 3, and there's algebra to be shown in 4. When you go over to the back, this is going to be what we have to do in order to get out our answers these are the questions that you're asked to answer on the back. They're supposed to be difficult and challenging. If you ever want to come in and see, we'll go over them together as much as you need to. You can stop in the math lab as well. But these are the questions that you need to be able to do with adequate notation, etc., to get yourself ready to take the exam. So that is due at the beginning of day 4. You also picked up another sheet. If we have time, we're going to go through it and touch on it. But looking at what we have, okay. Go through right now, please, and we'll check off today's date. Today's date is 9/29. The next thing that we're going to need to make sure that you all do is your homework. I'll give you the Math Excel stuff and activate it at the end of the period, so you have it. This is, for most of us, a little bit of a review and an extension beyond what we've done previously. Let's take a look, please. Go over to the next page. Take a look at what's there. And it asks you to start for the now, there's 2 different ways that you can go through and view slope. There's 2 different ways that you can go through and view slope. With non-calculus methods, you can go through and, if this is the graph of some function, if you're asked to go through and find the slope of it, the slope varies. Before there was calculus and a definite way to evaluate it, if I'm asking you to take the slope of this function at 1, you would need to go through and say, all right, well, I'm going to graph it out, and I can... Before you could determine the instantaneous rate of change, what you had to take was the average rate of change. And instead of being able to take the instantaneous slope right here algebraically, the algebraic way to get what the slope is to say, all right, I've got these 2 points here, to here and here. If I draw a secant line through it, or give me the slope between 2 known points on the graph, that would help give you an approximation to what the slope is at 1. So I pick 1 and 2 and find the slope of the graph between 1 and 2. That approximates it. But is that the most accurate way to find it? No. But what you have to do to make it more accurate is take this second point and keep making it closer and closer. So instead of, to determine your slope, let's say your derivative at 2, instead of taking the derivative at 2, we could take the slope at 2 points, and let's say when the slope is 2 and at 3, but there's a gap there. We keep tightening that up, so then I take it at 2 and maybe 2.5, 2 and 2.1, or then taking it at 2 and 2.001. See how each of those iterations, the slope keeps getting closer and closer together. The gap between the x's gets really, really small. And as that gap between the x's gets small, you get a more accurate representation of what the slope is going to be. It's sort of like in a manhunt, you're looking to find someone. You keep closing in on that value. And you might have it down to a mile radius, and then you get down to a half a mile radius, and then you get down to a quarter mile radius, and so on. And you keep narrowing it down. And with non-calculus methods, that's what you have to do. Now, for our stuff, what we need to make sure that you all know is this. To begin with, the average rate of change is the slope of the secant. So the average rate of change is the slope of the secant. Find the average rate of change of that function over that interval. So in order to find the average rate of change of that function over that interval, what we'll do is this. Let's evaluate out the function at the endpoints, because that's going to give you the change in the y values over the change in the x values. So when we're doing this, you're trying to find the average rate of change, or what the average slope is of the graph at those 2 specific values. So I go through and say that this would be equal to I have to check my notation to make sure that this is right, but change in y over change in x. So I evaluate out the function at 3 minus the function at -1 all over 3 minus -1. What is the function value, and this is one that we would be expecting you to do without the calculator. What is the function value at 3 going to give you? Hands up, please, if you can tell me. We'll wait for 6 of you. We need to know what the function value at 3 will be. We've got 1 person, 2, 3. We've got to be able to get this. 4, 5. Molly, did you get it? What I got? 42? 42. So 42 minus, now go through and evaluate out the function at -1. So you take 2 times, you take -1 squared multiplied by 2 plus 8 times -1. What's that value going to be? Mike, let us know what you get. -6. So 42 minus -6 all over 4. Now I go over to the numerator. And Leah, what's that numerator going to simplify to?
48.
Divided by 4. What's 48 over 4? So, the average rate of change is the slope of the secant line between those 2 points. Now, consider the rate of change of this function that's on the right-hand side there over, let's group this and shrink it, over those intervals from -1 to 2. So watch what happens in each of these intervals. I'm finding the slope from -1 to 2 first. And then the second time I find the slope, I'm looking at the slope from -1 to 1. Then I go -1 to 0. Then I go -1 to -0.5. What are all of those values as it's tightening down? What am I closing in on? The slope when? Slope of the graph where?
At -1.
At -1, because that's change, or that's staying the same. Everything else is changing. So watch what happens as I take my, here's the secant. So does that accurately approximate it? Kind of. It's not terribly inaccurate. But what's happening each time I bring this down to that slope? It would be, we go from this to something that looked like this, and then I drag this down again to here, and so on. Each time I get closer, my value or my approximation of the slope at -1 is getting more accurate. So as you close in on it and as you converge on it, as the gap between them gets really, really close to what value? What are we making the gap between those 2 points get really, really close to? 0. Remember, there's the limit definition of the derivative, which is the limit as h approaches what? 0. That's using out the limit process to take out your derivative. So what we're going to have you all do now is this. Let's have the first row here. You guys evaluate out the slope of this graph on the first interval, which is from -1 to 2. Second row, you're going to evaluate out the slope of this graph. You can use the function up top from -1 to 1. This row here, you're doing from -1 to 0. And this row here, you're doing this out from -1 to -1/2. So go through right now and determine what that's going to be. And by the way, you should be able to fill in almost all of this pretty easily. You know what the function's value at -1 is. You found it up above. Who in the first row got what that slope is going to be? 1 person? 2 of you? Did anybody get a different one? That was 10? How about the second interval? Second row, who got it? One person? Well, 8. Third row. Steve, what'd you get? Now, fourth row, you could use your calculator on this to figure out what it is at a half. Who in this fourth row got what that comes out to be? Noah?
4.
No? It's going to be 5. Now, what's happening as I get closer and closer to -1, the values are leveling off. And you can see, is this the most, well, this right here would be the most accurate representation of the slope because that's the smallest or tightest interval. The way that we find the average rate of change is to go through and take, actually, let's see, because I have this animated. Here's what the definition of the derivative is. If you take a point and you go above it, so you're adding to the x value and to the input value, that's our arbitrary h. You're picking some value and you're adding it to the input and then the function value as well. What's happening as you get closer and closer is that that's going to start leveling off. You can see when this resets itself, f of x plus h is out here. It's some h value. It doesn't matter whether you're going above or below it. As that h value starts getting really, really close to 0, you're going to get an accurate representation. And it's not anymore a secant line. It's an instantaneous rate of change because a secant line you need 2 points. An instantaneous rate of change is a slope at a single point. Now, that gets us down here. The instantaneous rate of change is the slope of a tangent line Now make sure, if you haven't already, go through please and sign into your calculators because all of you are going to do this. We're going to use a calculator to estimate the instantaneous rate of change of that function at -1. And we said estimate it. So I'll start off at -1. What value is really, really close to -1 that we want to go through and use? And there's more than one way, I guess, more than one value that we could pick. What's something that's really, really close to -1? -0.5, that's close. Who can get closer than he's at?
-0.9.
How about this? Like, do you want to be just at 0.9, or can you get really close?
0.999.
All right, so let's go to -0.9999999. Noin. 1, 2, 3, 4, 5, 6, 7. Let's make noin. Is that pretty close to -1? Yeah, we've got a really, really tight window here. So what we're going to need to do is I'm going to need to evaluate out the function at -1 minus the function at -0.9, 5, 6, 7, 8, 9, all over -1 minus -0.1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Now, your job is going to be this. Go into your calculators, and here's the down and dirty on this. Some of you don't know how to use these calculators very well at all. So again, make sure you've signed in if you have not already. Now, what we need you all to do is this. Go into your computation screen, go into a new document. You don't need to save whatever's in there. Now, what you're going to do is you're going to add calculator. You're going to put in what the function is, which is, what is it, 2x squared plus 8? Okay, so plug in whatever that is, plus 8x. Is there anything else on it, or no? We need to do a bunch of evaluations. So what you're going to need to do is control and then select the bar. Control equals and select the bar. And now we're going to do x equals -1. That evaluated out the function at -1. Now, you also need to evaluate out the function at negative point. No. So go back, -0.1, 2, 3, 4, 5, 6, 7, 8, 1. All right, and hit enter. So you get that value. Now, I would set it up, and actually, oh, hang on, maybe there's a way. Shoot. Oh, let's do this, delete this. Now, we need to use these values again. Well, actually, you know what, we can do this out kind of easy. Sorry, I didn't think we'd need it. Do control division, and do -6 minus. Now go up and select that value. And then in the denominator, what would we need to have? Tanji, what do you say? Yep. Minus, now, careful, I know that this is wrong already. But, oh, because you don't have enough, if you go up and select it and hit enter on it, there's a float issue on it. You see what I'm saying? Okay? So why is this input incorrectly? Hands up, please, if you can tell me what's input about this wrong. Yeah? Yeah, you want to have a negative in front. You could put it in parentheses. Now, press enter. Now, is this really 4? Go up and check. Select that. And hit enter. It comes out to be 4. And the only reason, now, is this exactly 4? No. We are so close, though, to it that the calculator isn't able to distinguish a difference. So we would go through and say that this is approximately, our slope is approximately, was it 4 or -4? 4, okay. Here's the limit definition of the derivative. And you all need to get very familiar with it if you are not already. Remember, the derivative is the formula for the instantaneous rate of change. So your derivative at x is going to be equal to the limit as h approaches 0 of the change in the function values over the change in the inputs. Now, this formula isn't given to you, but you definitely need to know what it is. There's actually 2 versions of it that we're going to go through and deal with. Get both of these down, and when we say that sign, that pound sign, it's not a hashtag. It is a symbol for a number. So, there's 2 ways that you can go through and give this out. This is called the slope, or this black equation gives you out what the slope equation itself is. You use the derivative to determine the slope at any point along the function. The second one evaluates out the slope at a specific value. So the notation matters. If you're using x's, that's going to give you out the equation of the slope as an answer. And that equation of the slope you can use to find the slope anywhere. The second equation is only used if you're asking to find the slope at a specific value. So if I'm asking you to determine the slope at 3, at 4, at 5, you could go through and use that. We're going to do both the first time through. Do we have both of those down? Use the definition to find the instantaneous rate of change. Let me separate this out. Use the definition to find the instantaneous rate of change of the f of x at -1. So the first time I'm going to go through and use the derivative of x is equal to the limit as h approaches 0 of the difference quotient, which is f of x plus h minus f of x all over h every time. Now I'm going to go through and say my derivative is equal to the limit as h approaches 0 of, now I need to take the f of x and plug in x plus h to it. So instead of this looking like it does now, I go back up, and some of you need to see there are two different input positions that I'm going to be plugging in x plus h into. All of those x's there are going to be getting replaced with an x plus h. So when we do this out, to start off, I always do brackets between them. So I'd say bracket, and then I'd say 2 times the quantity x plus h being squared plus 8 times the quantity x plus h. That takes care of the first part, the f of x plus h, minus, now from that I need to subtract the f of x. So, Abby, what is it going to look like if we subtract the f of x? What needs to be thrown on there as well? Minus the quantity 2x squared plus 8x, and then in the denominator, the only thing holding this up is an h. Can I evaluate out this limit by direct substitution now? No, because I'd be dividing by 0. You need to put the limit in front every step until you can plug a 0 in. The next thing I'm going to do is limit as h approaches 0 of, now I need to take x plus h and square it and then add 2 or multiply it by 2. Who can tell me what I did if I took the quantity x plus h and then squared it? We got 2 people, 3, 4, 5 of you, 6. What do you want to say? Hang on, don't multiply by the 2 yet. What do you get if you take x plus h and square that quantity? Now, x squared plus 2xh plus h squared, you need to do what to that? Good, so what would you write out? Now, let's keep going. What else would I be writing? Hannah, too? What would you say?
Plus 8x plus 8h, and then minus 2x squared minus 8x.
All over. As of right now, can I plug in a 0 for h and get an answer? Look at what's there, though. You should be delighted. Who can tell me why they're happy that they wrote all of this garbage out? What's the benefit of that? Evan? So let's go through and combine these and the 8x's. At this point now, I'm left with the limit as h approaches 0 of, now up in the numerator, I have a 4xh plus 2h squared plus 8h all over h. Well, that seems profoundly redundant to me. Because what did I just write a heck of a lot of? We got one person who sees it, 2, 3, 4. What do you see, Sierra, that you just wrote a bunch of? So what would you do? So let's reduce out the h's, and what are you left with?
4x plus 2h plus 8.
Can I now take my limit by direct substitution? This is the first step that you can. What do you get as an output? Valentino, what do you get as an output? What's that? Now, since you did that, you would now say your derivative equation is 4x plus 8. We need to evaluate out our derivative or determine what the slope is at what x value. Jack? What x value are we evaluating out the slope at? -1. So that would be 4 times -1 plus 8. What is the slope going to be, Catherine? In this process, you use the long definition. This right here is the equation of the slope anywhere. And then plug in a 1, or -1. Negative, sorry. Is that the only way we can do it? No. There's a little bit more direct way, but we're going to screw it up if we do it. Let's do Can I take this and lock it in place? Okay. Okay. The next way to do it, and it's a little bit more direct, is to use that second formula. Now, when you go through and use the second form, instead of having an x, you're going to say, all right, I know what the x value is going to be. So if I were going to use it, I would say this. I would say, all right, my derivative, and it was at -1, is that right? Is equal to the limit as h approaches 0 of f of 1 plus h minus f of 1, -1, minus f of -1 all over h. Now, in order to get out our answer, the next thing that we would need to do is evaluate out the function at -1 plus h. So that means, and maybe we need to do this in the margin, -1 plus h, so that means I would take 2 times -1 plus h being squared, and then was it plus 8x? We need to evaluate this out. So what do I get if I take -1 plus h and square it? Well, go through and let's find that out. This will be the limit as h approaches 0 of 2 times -1 plus h squared plus 8 times -1 plus h minus the function value at -1. Go in right now, hands up please when you can tell me what the function's value at -1 would give us. You should already know. What's this function at -1's value? Noah? What did we determine the function's value at -1 was?
4.
No. That's the derivative at -1. What is it? Not 6.
-6.
-6. Now, let's evaluate out what this is going to become. This is a more direct way, somewhat. Once we get to here, I say, all right, -1 plus h. If I square that, I would have -1 times -1 would give me a 1. Outside and inside would be minus 2h, then plus h squared. Now I can distribute out a 8, so this would be -8 plus 8h minus 6, minus -6, so it's plus 6 all over h. Look at the numerator. What is it going to be, Josh, after I distribute out the 2?
2 minus 4h plus 2h squared.
Minus 8 plus 8h plus 6 all over h. Let's put everything that we can together now. Notice in this, I don't have anything that directly cancels, but you do. You don't have opposite terms. What do you see?
2, -8, and 6.
So what's 2 plus 6 minus 8 going to give you? 0. And then everything that's left, what do they all have in common? What do they all have in common?
8.
Yeah. So now I go through and reduce out the h. So what am I left with after I get rid of that h value? Adam, what's the expression going to look like when you reduce the h out of what's here?
-4 plus 2h plus 8.
And now, can I evaluate this out by direct substitution? This is the first step that you can. Jake, what would you be left with when you plug in A, or make the replacement of h is equal to 0? Did they both come out with the same answer? Yes. The AP is very keen on giving you this with something plugged into it. They're very keen on using this and then you giving out what the equation is going to be. And you'll see that. I think there might even be one like that on your test or on your diving in. Next one up, write the equation of the tangent line there. So the equation of the tangent line, you have to use the definition of it until we tell you otherwise, because some of you know the shortcut rule, and that's fine. I need to go through and determine what the equation of the tangent line is going to be at that specific point. And you're lucky because we gave you the y value. We need to evaluate out what the derivative is going to be at a specific value. Which of the two formulas do you think I'm going to want to use? I guess it's up to you. Go back and look. There's two different ways we have to evaluate out the derivative, which is to determine the slope at an instant. Which one out of those two do you want to use? Hannah, what do you say? That's going to give us an equation for anywhere. Okay, so if you use that, you say your derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now I'm going to make my replacement in. And when I do that, Megan, what's it going to look like when I plug an x plus h in for the input in my f function? The quantity x plus h being squared, that's my outside function, minus the f of x. What's the f of x? And that's all over. So now I need to expand this out. Amber, what would you get if you expanded it out? I can do two different reductions now. What can I reduce out first, John? Gone. And what can I reduce out second?
BH.
So what am I now left with?
2x.
The limit as h approaches 0 of 2x plus h, which means your derivative would be equal to. And we need to go further and evaluate out that derivative at what x value. Katie? At 2. What would your slope be at 2? 4. This is the equation for the derivative anywhere. This is the way you would find the derivative at 2. You're still not done though. What's the equation of the tangent line going to look like, Sam? No, that's the equation for the derivative. Who can tell me what the equation of our tangent line is going to be, Scott?
I minus 4 plus 2x plus 2x minus 2.
That's what you say?
Say 1 minus 4 equals 4 times quantity x minus 2.
What's the slope of our tangent line? The slope that we need is 4. The point that we're using is 2, 4. Questions on that one? Now the next one that you need to know is the equation of the normal line, and I don't know if you've done this before. I think this is the first time you have seen it. Normal line is perpendicular to the tangent line. So knowing what you know, the normal line is perpendicular to the tangent line. Molly, what would you say the equation of the normal line then would be at that point?
Y minus 4 equals negative 1 over 4 times quantity x minus 2.
When is there a horizontal tangent line? Well, we need to figure out horizontal tangent line, if you're thinking about what this graph looks like, here's the graph of the parabola. Horizontal tangent line is going to be one that's flat going across, and it's going to have a, well, we'll say this. What is the slope of a horizontal tangent line? 0. We need to find when our slope is going to be equal to 0, and you can't eyeball it. So we know the equation to find the slope anywhere. We'll list it out. We'll list it out as our slope anywhere equation. We don't care about the slope anywhere. We're trying to find where the slope is equal to 0, because we would know that this has a slope value of 0. So we'd say 0 is equal to 2x. We'd set our derivative equal to 0. That's going to give you everywhere that the graph has a horizontal line of tangency, which is a huge thing because maxes and mins have that. You need to know this to figure out your local maxes and your local mins. Divide both sides by 2, you get 0 is equal to x. Now, it says when is there, when we're doing it. Sorry. When is the x? Where is the y? In terms of calculus, this is a big thing. Look, it's asking you when and where. When is the x value? Where is the y value? So when is this going to have a horizontal tangent line? When is the graph leveled off? It's when the x is equal to 0. If it said where, you'd have to go through and find out the y's. Now, the next one up, when would a curve not have a tangent line at a point? Think about that for a second. What kind of graph is not going to be, are we not going to be able to take a tangent line at or determine the slope at? What would that graph have? You're right, but then the function wouldn't exist there, so there's not a point there. Yeah, corners and cusps, things like that is when it gets really awkward. So here's a corner. So if this is my graph here, well, let's say when. So if there was a corner. The other one is if you have something like this. It's called a cusp. Think about that. You're not able to get an instantaneous rate of change there. Is that end for today? Yeah. So what we're going to do is this. Hang on just a second. Actually, let's do that. I actually don't know if this will work. Try this right now. Have those computer books that they give you out. I don't think this is going to work, but I'm not 100% sure. I don't think that this is going to work, but I'm not 100% sure. I'd rather us try and fail. Maybe your computers will do it. I know that mine won't. Go into Google Classroom. I know on my computer it won't work in Chrome, and that's the only web browser that you all have, is that right? Yep. Go into Google Classroom and see if yours Go into Google Classroom, please, and see if yours will work. Does it come up or no?
Wait,
Yeah, it says
this?
graphing link. Click on it. It won't let you. Yeah. Okay. Because see how there's this? You get a bunch, your screen right now looks like this. Is that right? Okay. I'll say this. Who has a different computer besides this one at home? Okay. I would advise you to do this. That link that's there is shared. It's a terrific graphing program. It's, I think, way easier to use than the one that you all have. By Paul Sieberger. I work with him over at MCC. He does terrific work. This is his graphing application. There's tons of stuff that you can do, but let's take a look at, and he does this for any function. So I think ours to begin with was y equals x squared, right? And I'll do this. We can make the background white, show the grid lines. You can right-click to make all of these things happen. I'll try to make my graph a little bit thicker. Control B, there we go. Now, it gives you, this is showing display only, but you can also go through and show out the tangent line, which is here. And the benefit of this, you can start playing around and see, what do you know about the derivative or the slope of the tangent line over on the right-hand side? What can you say about that, or those slope values on the right-hand side? They're all positive. What about to the left-hand side? What do you know about that? They're all negative. So, when the x's are positive, the slope or derivative is positive. When the when the x's are negative, the slope value, which has nothing to do with the y value, the slope value is negative. Well, in calculus now, we go through and say, yeah, I'm going to graph this out. I'm going to graph out what the derivative looks like. So, and you can do this because he made it so we can trace it and it'll show you what your slope is. When I go over here, like right here, what is the slope of the graph at 2? What's the slope of the graph at 2? 4. And every time I go further, it's increasing. Now, if you want to know what the slope of the graph is when your x is 19, it's going to be about 38. What they do is, and what we're going to be doing is, here is the graph. I'm going to graph out now the derivative and the tangent line. This graph that's in pink is the graph of the derivative. Remember when we were at the point 2? See how we said at 2 our slope was 4? So you would plot the point 2, comma 4. That's the graph of the derivative, not the function. Why is the graph negative over here? Why is this pink graph negative over there? No. The slope is negative there. What is the slope of the graph at, where was I at? At like negative, here. At negative 2, what's the slope? Negative 4, so we plot out the point negative 2, negative 4. Now, this is kind of cool to go, graph, okay, data grid. This is kind of cool because you can look at all different kinds of functions. That's the graph of the derivative. Where's our tangent line? No. So see, as I go across, see how this levels off with time, but it has a kind of big slope here? And you can play around with a bunch of different functions, like this one here. Notice, there's not going to be a, there you go. What is this called? A cusp. What do you know about the slope of the tangent line? It doesn't exist. Okay? So now, make sure you get your Math Excel homework. I'll activate it tonight before I leave. You can get rid of those computers. Good idea would be to throw them outside.